Okay, now you're about to learn a truly, truly amazing theorem. Okay, it's called the Fundamental Theorem of Calculus Part 1. Some books call it the Fundamental Theorem of Calculus Part 2, so it's pretty arbitrary whether you call it Part 1 or Part 2. Since our book calls it Part 1, I'm going to call it Part 1. So remember that before, or up until now, in order to evaluate a definite integral, we had to form the Riemann sum and then take the limit as n approaches infinity of that Riemann sum. Well, thanks to Newton et al. And the Fundamental Theorem of Calculus, we no longer have to do that. Okay, this amazing theorem says that if you have an antiderivative of your function, and your function is continuous between the limits of integration, then to evaluate the definite integral, all you have to do is take the upper limit of integration, plug it into the antiderivative, take the lower limit of integration, plug it into the antiderivative, and then the difference between those two is equal to the value of the definite integral. It's as simple as that. Okay, let's do an example here. So to apply the Fundamental Theorem of Calculus Part 1 to evaluate this, we need to find an antiderivative of 3x squared. Well, we know that x cubed is the function that we differentiate to get 3x squared. In fact, we have many, many of them, but the Fundamental Theorem of Calculus says we only need one antiderivative. So we're going to use x cubed as our antiderivative of 3x squared. So the Fundamental Theorem of Calculus says the integral from 1 to 2 of 3x squared dx equals the value of x cubed evaluated at 2, which is the upper limit of integration, minus the value of x cubed evaluated at 1, which is the lower limit of integration. Okay, so this is the intermediate notation you use. You put your antiderivative you're going to use, then you put a vertical line, you put the lower limit of integration, and you put the upper limit of integration there. So then we take the upper limit, plug it in for x, so we get 2 cubed, minus the lower limit of integration plugged in for x, 1 cubed. So it's equal to 8 minus 1, which is 7. Wow, can you imagine that? That quick to evaluate the definite integral. All right, let's do another one together. We want to evaluate the integral from 0 to pi of sine of x dx. So we need to start by finding an antiderivative of sine of x. We know that if we differentiate cosine of x, we get negative sine of x. So that means that an antiderivative of sine is going to be negative cosine of x. That way this negative is canceled when we differentiate this to get negative sine of x. Okay, so this is negative cosine of x evaluated from, so this is our interval of integration, 0 to pi. So we get negative cosine of pi minus negative cosine of 0. So that's equal to negative cosine of pi is negative 1 plus cosine of 0, which is 1. So we get 1 plus 1, which is 2. Okay, so the value of the integral from 0 to pi of sine of x dx is 2. Okay, why don't you press pause and try this one on your own? So the simplest antiderivative to use in this case is the antiderivative of x cubed, x to the 4th over 4, and an antiderivative of 1 is x. Now we just take this 3, plug it in for the x's, and subtract off what we get by negative 1 plugged in for the x's. Okay, so if we put all this together, we get 24. Okay, so that's the value of the integral from negative 1 to 3 of x cubed plus 1 dx. And that is the Fundamental Theorem of Calculus.